What to say about vectors? Well, lots of things, and also not a lot, really, in some ways. So, what is a vector? Well, at a very kind of basic level, it's just a direction and a length, or I would say a direction and a magnitude, which is just the fancy word for length. But usually it's not very convenient to describe a vector in that way. Right? If I said, for example, my vector, let's say the vector v has direction, the let's make it, I don't know, 60 degrees counterclockwise from the positive x-axis. That's a whole mouthful right there with a magnitude of 2. We could draw that. I'm going to draw it in kind of the typical way where you draw your vector starting or originating from the origin because that's easy. So I'm saying, okay, well, 60 degrees is like that. So maybe my vector looks like that. It has a length of 2 and an angle of 60 degrees. But that's not a very convenient way to describe it because it takes a whole lot of words to write that. There's a much nicer way of describing it by talking about what the components of the vector are. So I would say, well, we can find the x and y components by using trigonometry here. The vector v has an x component of, well, let's actually find it. It's going to be 2 times cosine of 60 degrees because cosine of 60 is equal to the length we're trying to find divided by 2. And similarly, the y component or the vertical component is going to be 2 times sine of 60 degrees. And then cosine of 60 degrees is 1/2. Sine of 60 degrees is root 3 over 2. So this vector happens to be the vector 1 comma root 3. And that's a perfectly fine way of writing it. But there's probably like 5 ways people like to write vectors, and nobody happens to agree which way is the best. I will probably typically default to writing it using this bracket notation. So I feel like that's pretty standard. But another equally good way of writing this would be to write it as 1 times I plus the square root of 3 times j. Because ij, and we'll talk about k in a minute here, I is the unit vector in the x direction, meaning it's a vector having length 1. In the x direction. And similarly, j is the unit vector in the y direction. So let's talk about how we really want to talk about vectors, which is, let's say I want to ask a few things like, what is the length of the vector? What have I got here? Sure. 2 comma 4 comma 6. Okay, well, we need to talk about magnitude here. The idea of magnitude here really is just abusing the Pythagorean theorem. That's all it really is. Or really, alternatively, you can think of it using the distance formula because the vector 2, 4, 6 is the vector that starts at the point, well, the easy choice is the point 0, 0, 0, and then we draw it over to the point 2, 4, 6. There's the vector we're looking for that originates at the origin and terminates at the point 2, 4, 6. I will point out, that's a point using parentheses. That's a vector using brackets. So that point is 2, 4, 6. This vector is the vector bracket 2 comma 4 comma 6. And the way to find the length here, or the magnitude of the vector, some people like to use just single absolute value symbols, essentially. Some people like to use doubles. They're fairly interchangeable. But what you should recognize that is if you see this or this, the fact that it's a vector means you're not taking an absolute value. You're finding its length, its magnitude. So whether they're using double absolute values or single absolute values, you have to find the length of that vector, which is going to be the square root of 2 minus 0 squared plus 4 minus 0 squared plus 6 minus 0 squared. Which in this case is going to be the square root of what? 4 plus 16 plus 36, which is the square root of 56. Now, really, we didn't need the zeros here because any vector that terminates at the point 2, 4, 6 and started at the origin, we know it's starting at the origin. So more generally, if your vector v has components, say, a, b, and c, then the magnitude of that vector is going to be the square root of a squared plus b squared plus c squared. This class, we typically are limiting ourselves to things that like really exist in the physical world, right? Like vectors in 3 dimensions or in 2 dimensions. But you can talk about vectors in 4, 5, 6, any number of dimensions. And the nice thing is most of these definitions we're talking about hold, meaning if you wanted to find the length of a vector that was 5-dimensional, it would just be the square root of a squared plus b squared plus c squared plus d squared plus e squared. Whatever the components are, squared add together. So that idea is going to persist, as will most of these ideas. I think the cross product is an exception to that when we get to the cross product. But most of these ideas work for vectors in any number of dimensions, which you will talk about when most of you take 22A, right? 22A, talking about matrices and vector spaces and stuff like that. And you can have we'll talk about vector spaces of dimension higher than 3. So when you start thinking about higher dimensions, some people would say they can like visualize 5-dimensional garbage, whatever. But really, dimension doesn't have to be like a direction in space. It can be an attribute, right? Your 5 dimensions can describe the 3 components and maybe what time it is and what color it is, right? It doesn't have to mean like physical like displacement in space. Make sure I'm keeping on track here. So often we want to find a unit vector, which I know I've said twice and maybe I haven't defined, in the same direction as v, which is again the vector 2, 4, 6. So a unit vector is just a vector of length 1 or magnitude 1. So real quickly over here, a unit vector is a vector of length 1. Or magnitude 1, whatever word you like. We will use those words interchangeably. The way you typically create that is you take your vector that points in this direction, and then you divide that vector by however long it is. Right? If that vector has a length of 5, whatever direction it points, if you divide this thing that's length 5 by 5, you get something pointing in the same direction that only has a length of 1 anymore. So the typical process here to normalize a vector or to make it have a length of 1 but still point in the same direction is to divide it by its own magnitude. So here, our calculation would be the vector v divided by the magnitude of v, which is going to be the vector 2, 4, 6 divided by the square root of 56. And there's probably like, I'll say this a lot, there's probably like 3 ways people like to write this too. I would probably prefer to write it as 1 over root 56 times 2, 4, 6 as a vector. But some people actually like to distribute that value through. I don't find that particularly nice, but you can write it like that. I feel it's annoying, especially when your thing you're dividing by is irrational. So you can write it as 2 over root 56, 4 over root 56, 6 over root 56. Yeah. Trajectories. You mean like vector value functions? Yeah, we're definitely going there eventually. Maybe not today, but yeah, yes, that is we're definitely headed down that path. No, no. The path, it's like the path that you okay, fine. All right, so one thing that is useful to know, even though I know where I said it, is a vector is a direction and a magnitude. So what you sometimes have to actually do, even though it might not feel like it makes a lot of sense at first, is we can express the vector v as its direction vector multiplied by its magnitude. Now it's going to look real stupid because all you're going to do is take this unit vector and multiply it by root 56. So it's going to look like, yeah, the vector v is its magnitude, the square root of 56, times the unit vector, which again is 2 over root 56, comma, 4 over root 56, comma, sorry, I can't quite see that, apologies, 6 over root 56. But there is usefulness here because later on we're gonna like not know stuff about the vector, and it's gonna be really useful to be like, oh yeah, remember we said you can always express a vector as its direction vector, which is a unit vector, and its magnitude times its magnitude. So even though it seems kind of silly at this moment to like, why would you write it like that? There is use for this later on. Something else I really want to say here. I know what it was. So I will point out. So here's, and some people call this like V star. I would probably usually call this U if I hadn't already used the letter U, U for unit vector. So here's my unit vector U pointing in the same direction as V, but having a length of 1. If someone asks you to describe the direction of a vector, in many people's opinions, you don't actually have to find the unit vector, right? This vector, 2, 4, 6, is still telling you the direction it points in. The reason why we do this is because I don't want all 12 of you to give me 12 different answers. When I ask for the direction vector, I don't want to hear 2, 4, 6, 4, 8, 12, 3 times it, 10 times it, because all those vectors do point in the same direction. Any multiple of a vector is still a vector that points in the same direction. So to kind of standardize the responses we get, and for other reasons as well. But a lot of it is to say, I want you all to give me the same answer when I ask for what direction does this vector point in. And so the typical standardized way of doing that is by normalizing the vector, turning into a unit vector with a length 1. So typically, when you get asked to find the direction the vector points in, your standard answer should be, oh yeah, it's the unit vector that's pointing in that direction. So dividing whatever answer you've got by its own magnitude. All right, let's see here. Yeah. So the problem with this part here is a lot of people have probably already seen the stuff we're going to do, and it feels a little bit like it's super easy, but we should still talk about it because we have to make sure we all know. We will go through it kind of quickly. So vectors we have in 2 dimensions or 3 dimensions. I'll remind you all, I know I said that the unit vector I is 1, 0, and the unit vector J is 0, 1. But it's also appropriate to say that the unit vector I is 1, 0, 0, and J is 0, 1, 0, and K is 0, 0, 1. And really and truly, these 2 vectors, this I here and this I here, those are the same vector. It's just one of them is including a 3rd dimension to make you aware of the fact that we're writing these vectors in 3 dimensions. But literally, these are the same. They both point 1 in the x direction. It's just one of them I'm drawing in the XYZ coordinate plane. So let's look at some vectors. Let's say that we have W equal to the vector 3i plus j, and V equal to the vector I plus 5j. And when you read this, you should just think, okay, 3i plus 1j just means over 3 and up 1. And I plus 5j just means over 1 and up 5. Maybe, in fact, let's make it negative I plus 5j. That means it's going to be left 1 and up 5. It would be just as good to write this as 3, 1. It would be just as good to write this as negative 1, 5. you definitely should try to develop a level of comfort with going back and forth between these ways of writing vectors. Another way someone might write this is as a column matrix. All these are perfectly good ways of writing vectors. And annoyingly, some people use parentheses. Hopefully none of your instructors do because it's really annoying because parentheses we usually reserve for points, not vectors. But some people do use parentheses to write vectors. I don't know why. Okay, anyway, what is W plus V? Well, the nice thing about adding or subtracting vectors is it works the way you think it should work. You're just going to add the corresponding components together. So if I want to do 3i plus j plus negative I plus 5j, it's kind of nice when you write it this way because you can kind of think of like I and j as variables and you're just saying, oh, okay, I have 3 of that variable and negative 1 of that variable, and I'm going to add those things together and get 2 of that variable. It's just the variable is actually not a variable, it's representing a direction. So here, 3 plus negative 1 is 2 in the I direction, and j plus 5j is 6 in the j direction. What's also really nice about vector addition and subtraction is that it has a very nice kind of physical interpretation. So when you're adding vectors, geometric is what I was trying to say, geometric interpretation. So if I draw both of these vectors, and again, we usually like to draw vectors originating from the origin, although they can start anywhere. And I think in someone's notes, it says something about like how any vectors that point in the same direction and have the same length are the same vector. Even if they're one starting here, one starting there, and they point that way, they're the same. Doesn't matter where they start. It just matters how long they are, what direction they point in. That's all that matters when you're talking about a vector. So here, if we draw these, I guess I need some points here. 1, 2, 3, 4. 1, 2, 4, 5, 6. 1. Let's see. If I want to draw 3i plus j, and let's use some colors here. My w vector is going to be over 3 and up 1. So there's my vector w. Whereas my v vector is going to be left 1 and up 5. Looks like that. And if you want to add w and v, you just put one of their tails on the other one's head. So I could draw it by translating v over here. So let me make sure I get this right here. So there's also v, or here's also w. And the vector that starts at the origin and ends at where v plus w ends, that is the vector v plus w. And it terminates exactly at the point it should, 2, 6. That's kind of hard to see. Let me zoom in a bit here. Sorry. Much better to see. So, right, v plus w or w plus v, right? Order of addition doesn't matter here, right? Or you say addition is commutative. V plus w equals w plus v. In this case, equals 2, 6. And occasionally we use this fact that you can add the vectors by putting them on top of each other like that. Has everyone gotten the attendance sheet? Cool, you can just leave it there, it's fine. All right, so vector subtraction, on the other hand, always feels weird to me. Not weird, just I always have to remind myself like the trick of drawing it. So I can never just draw it the right way without thinking about it, which is not a bad thing. So if I wanted to find instead, I don't have enough room. Let's not try to squeeze it in over here. Do I want to? Let's try to say, what if instead I wanted to calculate W minus V? Well, calculating is the easy part. W minus V is just going to be 3i plus j minus negative I plus 5j, which is going to be 3i plus I is 4i, j minus 5j is minus 4j. Graphically, for me, it's always harder to see what it is. So here's what I'm going to show you, and then we'll do the trick. So I'm still going to draw the same vectors. I could almost fit it in there. No, don't do it. Resist temptation. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 1, 2. Okay, cool. So let's see here. Here's W again, over 3 and up 1. And here's V again, left 1 and up 5. Up 5, yeah, up 5. And so if I want to calculate W minus V, well, what I'm going to think of, because that's the way my brain works, is I'm going to think of, oh, W minus V is really W plus negative V. So negative V is the vector that points in the opposite direction of V, the same length. So there's V pointing that way. Here's negative V pointing, in fact, right, we can calculate it. Negative V is negative I plus 5j, which is positive I minus 5j. So I'm going to go 1 right and 5 down. I knew I needed to go further down. They should point in exactly the opposite direction. So they should form a straight line. So there's my negative V vector. And now I can add W plus negative V in the way I added W plus V before, by either putting negative V over here, like that. And let's make sure I end up at the right spot here. Yeah, that should be about right there. Or by doing negative V and then tacking on W right there. So this vector originating here and ending here is our W minus V, which now I can see what it's supposed to be. Oh yeah, I'm supposed to just take this and I'm going to scooch it. I'm going to slide it right over here. So it's really the vector that starts at V, or starts at the head of V and ends at the head of W. So that is also W minus V. But I never remember that trick until I've drawn it, because I just don't. But I think it's pretty easy to see that that has to be W minus V, because, well, if V minus W is equal to that vector over there, let's call it U for a second. Then if I add W to both sides, it should be true that V is equal to U plus W. And certainly, I don't know. Oh, I wrote the wrong thing. Sorry, I wrote V minus W, and that's not what I have. I have W minus, right? W minus V, not V minus W. Sorry, apologies. Let's try that one more time. If we say that W minus V is equal to U, and then we isolate W, W is equal to V plus U, which is certainly what we've got, because we first do V and then do U, V plus U ends up giving us W, exactly as it should over here. I don't think knowing these like geometric things are super duper important. Like, it is good to know that when you add vectors, you just like put one on top of the other essentially. And we use that sometimes, but like not a whole lot. It's it's more important, I think, to know that you add vectors in the nicest way possible by just adding the components together, which is great. Also, by the way, when you do take 22 later on and start adding matrices together, the same kind of thing applies, in that when you add two matrices together, as long as they're the right size, you just add them the way you would hope to add them, meaning the components in the same spots get added together, and you just add all the things together really nicely. What else do we have here? Oh yeah, let's do one more thing here. Yeah, sure. Let me make sure. Let me zoom back out a little bit. Sorry, before I get too crazy here. Yeah. So to find something like, say, 2W minus 3V, well, vectors multiplied by scalars, you just distribute the scalar through. So in this case, I forgot what my W and my V were. My 2W is going to equal 2 times 3I plus J minus 3 times my V is negative I plus 5J. So it's going to be 6I plus 2J plus 3I minus 15J, which is going to give me 9I minus 13J. And you could draw it. I don't really want to, but you could draw it by saying, okay, well, my W was, this is going to be kind of gross, but fine. So let's see, W was over 3 and up 1. And my V was again left 1 and up 5. So then if I wanted to do 2W minus 3V, well, here's my 3V in this, my minus 3V going this way. Let's see, 1, 1, 2, 3. Sure, that's close enough. And here's my 2W. I'm going to extend this out further. Double that. So here's my 2W. Here's my minus 3V. And then you again, just you add them together in the same sort of way. So we're going to end up, really test your ability to draw parallel lines. Pretty good. Feel pretty good about that. It seems not unreasonable that this final vector over here, which is our 2W minus 3V, that certainly seems like it could be the vector 9I minus 13J. I don't know why I tried to write it like that. Sorry. Right, I've gone over 9 down 13. Yeah, seems plausible. So you can actually like add vectors geometrically by just like taking in however many of them you're doing in one direction, however many you're doing in the other direction, and then like putting it together like that. And you should be able to get a reasonable looking result that's actually showing you like, okay, this final vector is pointing right and down, more down than right, and kind of big. What's the magnitude of that vector? That's an interesting question. So if I want to find the magnitude of 2W minus 3V, you really shouldn't try to think of it separately. Like you should do what we've already done, put it all together to get some nice simplified vector in IJ or 9 comma negative 13 as bracket notation, and then just write it as the magnitude of 9I minus 13J, and then that's going to be the square root of 9 squared plus negative 13 squared, which is something as what? 81 plus 169, so 170 plus 80 is 250, square root of 250. But you shouldn't simplify it. I mean, maybe you should, I don't know. Okay. Yeah. Which way to go now? So time flies. Let's see here. Lots of things. Okay, yeah. So let's go ahead and talk about kind of the next vector operation. So addition is fine, subtraction is fine. Multiplying a vector by a scalar, also totally fine. They all work very normally. On the other hand, multiplying vectors is a different thing entirely. So how do we multiply vectors? Good question. Well, depends. Depends on what someone said. There's actually so I should point out for vectors in 3 dimensions or less, meaning not 4-dimensional or 5-dimensional, there's one way that's only good for 3-dimensional and 2-dimensional, which is the cross product. There's also something called the dot product. So we'll talk about both of those. We'll talk about at least one of them today. So we're going to talk about the dot product, also known as the scalar product. It's called the scalar product because when you multiply vectors together in this way, the result is a scalar number, not a vector. On the other hand, there's also something called the cross product, which is also called the vector product. Because when you take the cross product of two vectors, you do get a result that is a vector, which is really kind of important in this class. But let's talk about vectors first, or dot product first. So to find the dot product of U and V, we calculate the following. U dot V. When you write U dot V, make sure you emphasize that there's a dot right there. Don't just write U next to V like you would normally write regular multiplication. Make sure that dot is bold. So the way you're going to calculate U dot V, well, if you happen to know the angle between U and V, which we usually won't, but if you do, you can calculate the U dot V as the magnitude of U multiplied by the magnitude of V multiplied by cosine of the angle between these two vectors. And this is really how we define the dot product. But it's not how we usually really calculate the dot product. And I forget which class I saw the notes from which was it, Luli, I think, who does nice. He actually, in fact, I'll show you guys in a moment here because I think it's actually a nice explanation of where the dot product kind of actually comes from. But really, what we actually do is if we know the components of U and V, so if U is equal to like the components U1, comma U2, comma U3, and V is equal to V1, comma V2, comma V3. Or I'll say for dot product, as many components as you want. This would work if you had a vector with 4 or 5 or 17 dimensions. All we're going to do is multiply the corresponding components together and add up the results. So U dotted with V is equal to U1 times V1 plus U2 times V2 plus U3 times V3. Where does this come from? It really comes from like the law of cosines. I do think it's kind of neat to see this, but I don't want to get too into the weeds with it. But let me show you this handout from Luli. I'll give you a moment before I cover up the screen there. So let me show you this, just because I think it's neat. Like I was like, oh yeah, that's true. I just never really thought about that much. So who remembers the law of cosines? Everybody, right? So the law of cosines is essentially the more general version of the Pythagorean theorem. So if this triangle was a right triangle, yeah, sure. If that angle theta was 90 degrees, then that C side would be your hypotenuse side. And you say the length of C squared is equal to the length of A squared plus the length of B squared minus 2 times the length of A times the length of B times cosine of pi over 2, which is 0. So if theta is equal to 90 degrees, you actually get the Pythagorean theorem here. But if theta is not equal to 90 degrees, this is the more general version of the Pythagorean theorem, which says, okay, you can actually calculate the length of any side of a triangle by knowing the other two sides and the angle between them. By saying, okay, the length of C squared is the length of A squared plus the length of B squared minus 2 times the length of A times the length of B times cosine of theta. And then he actually shows you like how you can calculate this. Well, if we say that C is A minus B, right, it is. Remember how we just talked about how vectors are subtracting here each other? Or I would say B plus A minus B is A. Say that again. B plus A minus B, the B's will cancel out. B plus A minus B, the B's add to 0, and you're just left with the vector A. So C really is the vector A minus B. And then if you write C like this, well, we're going to calculate the length of C squared in the usual way. The magnitude of a vector is just the square root of each component squared added together. So that magnitude is, the first component of C squared plus the second component of C squared plus the third component of C squared. And then we're not taking the square root of it because we are squaring the magnitude. Okay. And then it's just a bunch of algebra. Yeah. Oh, and the law of cosines? No. That's a fair question. Like, where does that cosine come from? So, not right now, but I can definitely either show you or point you towards a proof of the law of cosines later on. But it's not too hard to prove the law of cosines. It involves using the angle sum or angle difference formula for cosine or sine. But it's definitely, the law of cosines is definitely true and not too hard to prove with geometry and trigonometry. This here, I'll point out, right? So this is totally this. And then all we're doing from here is we're just multiplying it out. The A1 minus B1 squared is this first part. The A2 minus B2 squared is that first part. This notation is terrible. The A3 minus B3 squared is this part here. Add it all together, and well, the A1 squared plus A2 squared plus A3 squared is exactly the magnitude of A squared. Same thing for the B1 squared plus B2 squared plus B3 squared right here. And all of this comes out to be all of that. But then essentially what's happening here, is this part here is exactly the same as that part up there. So, oh yeah, the definition of the dot product here of what can I help you? Okay, well, I hope you find it. So the thing that we said was the dot product of A and B is actually equal to A1 times B1 plus A2 times B2 plus A3 times B3. It's kind of neat. I think it's really neat, actually. Do you need to know this? Well, I was gonna say no, but maybe you do because like some of your instructors seem like a little bit intense about some of this stuff. So maybe you do need to know this. I don't really think you need to know it this hard, but it definitely you do need to know that there are two ways of thinking about and calculating the dot product. The way we don't usually do it, but is the way we define it, because often you don't know the angle between the two vectors. And then the way we usually calculate it. I was doing something, and there we go. This. Now, what's kind of neat about this is you can actually use the combination of these two ways of calculating the dot product to find the angle between any two vectors. So if we set these two things equal to each other, or in fact, not even just knowing that we can write this like that, you can say, well, then U dotted with V divided by the magnitude of U and the magnitude of V is equal to cosine of the angle between them. Which means then you can find that the angle between two vectors is exactly equal to the inverse cosine of the dot product divided by the magnitudes. And probably the most important fact here is that, maybe not most important, a very important fact is that if the dot product of two vectors is equal to 0, then we know that those two vectors had to have been perpendicular to each other. This is only true if U is perpendicular to V. Because for that thing to be equal to 0, you have to have had that cosine of theta was equal to 0, which means the angle had to have been 90 degrees. And we use that fact a lot, like all the time. So one thing we could ask is to say, find a vector perpendicular to V equal to 5, 5 comma 2 comma negative 3. And when your vector is a vector in R3, which will, right, that's three-dimensional space, R3, it's actually really easy. It's actually almost too easy because you actually have an infinite number of options. Let me show you three real easy ones. One answer to this would be W equal to 2 comma negative 5 comma 0. One real easy answer, which usually people exclude, would be R equal to 0 comma 0 comma 0. This is not a good answer because although technically those vectors are perpendicular, they're not really, even though the dot product is 0. Because this vector here, this is the 0 vector. And the 0 vector is the only vector that has a length of 0. It's not really a great vector. It's kind of missing out on what makes a vector because it doesn't really have a direction either. What direction does the point in? It doesn't, right? It's got no length to start and end at. So the 0 vector is a vector and it is useful for things, but it's not really good at pointing in a direction. So if someone ever asks you to find a vector perpendicular to another vector, your answer usually they'll say that has a length not equal to 0 or is greater than 0 or isn't the 0 vector. So this, not a great answer. However, if your instructor isn't careful and they ask you to find a vector whose dot product with another vector is equal to 0 and they don't say you can't use the 0 vector, I mean, that's an option. But make sure you read the question carefully so you're not like saying something you shouldn't be. But there's like at least two other easy answers here. You could say the vector x. So the usual way you find the vector perpendicular is you switch two components, change the sign of one of them, and then make the other one 0. So you could also do something like 3 comma 0 comma -5, or you could do what? 0 comma 3 comma +2. All those would work. Or you can come up with something completely different. You can come up with something like 1 comma -1 comma 1. That would also work because 1 times 5 plus -1 times 2 plus 1 times -3 is 5 minus 2 minus 3, which is 0. So there's lots and lots and lots of vectors that are perpendicular to this vector. In fact, this is something we're going to do later, but I'll talk about now. For this vector v, there's an entire plane of vectors that are perpendicular to it. This vector in the plane, that vector in the plane, that vector in the every vector in the plane that's perpendicular to that vector is perpendicular to that vector. On the other hand, if your vector lives in R2, like say your vector is 3 comma 4, there's only really 2 good options for your perpendicular vector. I mean, there's still technically an infinite, but one perpendicular vector could be, say, 4 comma -3 or -4 comma 3. But really, there's not a lot of options here. I should write more words. This vector is perpendicular. It's not really all of words. What else do I want to say while we have time here? Sure. Let's go ahead and talk about the other thing as well. So, actually, I know what I want to do. So, yeah. Let's go ahead and find the angle between the vector 1, 1, 0 and 1, 1, 1. Which might not sound like that interesting a question, but if you draw it, it's kind of like you're finding the angle between, let me draw this the right way, sure. The main diagonal of a cube and the diagonal of a square. So like, here's your vector. That's your vector 1, 1, 0, because you've gone one that way and one that way. So let's call this one V. And here's your vector 1, 1, 1. Which I'll call W. And I really would like to know what that angle is there. So when I do this, finding the angle between two vectors, I never start off with theta equals the inverse cosine of whatever. I would always prefer to start off with saying the cosine of my angle is equal to, in this case, V dot W divided by the magnitude of V times the magnitude of W. It just feels nicer to write. In this case, that's going to equal, let's see, V dot W is going to be 1 times 1 plus 1 times 1 plus 1 times 0. And the magnitude of V is going to be the square root of 1 squared plus 1 squared plus 0 squared. And the magnitude of W is going to be the square root of 1 squared plus 1 squared plus 1 squared. So it looks like we're getting that cosine of our angle is equal to 2 over root 6. Or rationalizing that, 2 root 6 over 6, or root 6 divided by 3. Which is not a nice value as far as angles go, right? I don't know what angle you take cosine of to get root 6 over 3. But we could plug that into a calculator and say, well, I know that, well, in fact, here's what I would write. If I was asked to find this, I would say my angle is equal to the arc cosine or the inverse cosine, whichever way you want to write it, of root 6 over 3. And that's actually my final answer. But if someone asked me, well, approximately what is that really? Then I would use a calculator and say, okay, well, the inverse cosine of root 6 over 3. Now, before we answer this question, do we think our angle should be more than 90 degrees or less than 90 degrees? Right, looking at the picture, it seems like less. But if we didn't have the picture, how would we know it was still less? Well, if cosine is equal to a positive number, the angle had to have been in quadrant one or quadrant four. But quadrant four is a silly answer because you're not going to say the angle between two vectors is like 300 degrees. You're going to say it's 60 degrees. So here the angle has to be acute because cosine is equal to a positive number. If cosine was equal to a negative number, the angle would have to be obtuse, somewhere between 90 and 180 degrees. So here we end up getting approximately 35.3 degrees. It's kind of neat. There are some interesting questions people ask about like the angles between atoms in the molecule because the molecule is like molecule, I forget which one it is, but there's like one that's like kind of like a tetrahedron shape. And so you can totally use this idea to find the angle between atoms in a molecule that are like symmetric. Oh yeah, that's kind of cool. I mean it's neat. Is it super useful? I don't know. I don't know. Maybe it really is useful to find the angle between atoms in a molecule. I don't know. Maybe I don't know chemistry at all. Like maybe that's something that's really useful and there's lots of applications for it. Okay. The last thing I'll say is the cross product. So the cross product, even though I feel like we usually wait a little bit longer here. So for now, we're not going to talk about like the way you usually actually find the cross product. We'll talk about kind of more what it works out to be. So if you have two vectors u and v, u cross v, and now here's something that's interesting about the cross product. Unlike almost any other operation between two things you've seen so far, like addition, multiplication, the cross product of two vectors is not commutative. If you change the order in which you do it, you don't get the same result. Now, specifically, the cross product is actually anti-commutative, meaning if you do v cross u, it'll be the negative of u cross v. We'll see that more later, but I just want to point that out. That it's kind of the first thing we see that where if you multiply in the opposite order, you don't get the same result. You will also see that when you talk about matrices in 22a. When you multiply two matrices together, if you do it in the opposite order, the result is wildly different. And it's not just anti, it's a completely different thing. So here, the way you could calculate the cross product that you're never going to do probably is the magnitude of u times the magnitude of v times sine of the angle between the two vectors. But that's not quite it. That right there is just like how long your vector is. Then you're going to have to multiply it by the vector n, where n is a unit vector perpendicular to both u and v. I should say one more thing, as determined by the right-hand rule. Which I think I have mentioned before, but I'll mention it again. So that's why it's anti-commutative. So if your vector u points that way, and your vector v points that way, and we're imagining like we're in the xy plane, well, if you put your fingers in the direction of, so hold on. If you hold up your right hand, that's why it's called the right hand rule, because you have to use your right hand. If you put your fingers in the direction of u and curl them in the direction of v, your thumb should point in the direction of the cross product. So here, u cross v should point upwards if we're imagining like that these are living in the xy plane kind of. There's u cross v. And on the other hand, v cross u would point downwards because you put your fingers in the direction of v, so I can kind of like go like that way, and I can't curl them that way. I have to turn my hand over to curl in the direction of u, then my thumb point downwards. Right, it feels weird to kind of go the wrong way, but that is what happens. So our v cross u would point downwards instead of upwards in this particular example. Yeah, so I'll say one more thing and then I will stop. So I'll just point out like for your unit vectors in the x, y, and z direction, you have, your unit vectors I, j, and k, it's going to be the case that I crossed with j is equal to k, j crossed with k is equal to I, and k crossed with I is equal to j. And if you do it in the opposite order, j cross I is going to be negative k cross j is going to be negative I, and I cross k is going to be negative j. And you can use this to then find any other cross products because essentially you have like a commute or not, you have like a distributive and an associative property. So like if you want to say, for example, like 3i plus 4j crossed with 2i minus 3j plus 4k, you could just then essentially multiply the whole thing out terribly and then use each of these properties. So like this is going to be 3 times 2 is 6 times I cross I plus 3 times negative 3 is negative 9 times I cross j plus 3 times, okay, oh my God, this is terrible. I cross, and so on and so on. I don't want to do the rest because you should never do it this way. I should say one more thing. I know I keep saying one more thing. I'll just say one really last thing. A vector crossed with itself is zero. You don't get anything. I crossed with I doesn't give you anything. And we'll talk about that next week. Yeah. Oh, and I know that there's a good reason why, because of this, right? Because I cross I is equal to the magnitude of I times the magnitude of I times sine of the angle between those two vectors, which is zero. And sine of zero is zero. That's how you get zero.